So over the last couple of years, Docker has definitely made an impact in people's lives. It's changed how we can deploy applications onto Linux. Conferences like ourselves have got some awesome speakers talking about how we can change deployments, make everything more scalable and easier, and how wonderful the world of Linux is. Yet for those of us who are still in the Windows-focused world, it's not been such a great story. Like we didn't have containers, we didn't have such a deployment strategy, and everyone in the Linux world was having so much more fun. Well, thankfully, with the arrival of Windows Server 2016, that has now changed. Windows containers are now native. They're part of the operating system itself. And so we can have all of the fun which Linux containers are having, yet deploying our Windows-focused apps. And so this is what I'm going to be talking about today. And I want to introduce what containers are as a concept, but more particularly how they apply to Windows and what benefits and value that brings. So my name is Ben Hall. I am the founder of a company called Katacoda. Katacoda is an interactive learning platform for software developers. We host interactive environments that are accessible via the browser, and these are pre-configured with Docker, Kubernetes, and very soon Windows containers. And so you can experiment and play around without having to download or install anything. And to give you some tips and hints, and so you know what you need to learn and what's important, we include step-by-step tutorials, and so you can follow those along and learn all of the skills and technologies which I'm going to talk about today. So what am I actually going to talk about? Well, I'm going to start with an introduction into building and deploying Windows containers. I'm going to compare this to how it looks in the Linux world, for those who are familiar and kind of played around with Docker and Linux. Look at Hyper-V containers, which are slightly differently, how we can start deploying containers at scale using things like Kubernetes and Swarm, and then finally look towards the future and where I think the container landscape is going. So before we get into this, let's take a step back and let's look at what containers are and look at where containers are important. And if you think of where we are previously and before what we had containers, we're generally dealing with virtual machines. And as I'm sure many of you are very aware, virtual machines have many different problems. They're very big, they're very heavy, they're resource intensive. Every time we wanted to deploy a very simple .NET application or a very simple Node application, if we wanted to run that in a sandbox in isolation, it would have to have a virtual machine wrapped around it. But in order for that machine to run, we'd have to have a guest operating system. And so we'd have to pre-allocate 4 gigs of RAM, certain amount of disk space, certain amount of kind of resources in order just to have that node process in a secure, stable way. And this kind of had overhead, but it also had slow boot times, which made it difficult to scale up dynamically because we'd have to wait for our EC2 machine or Azure machine to boot up. It was slow to build and maintain and keep up to date, and generally it just wasn't that fun. And so what containers have started to do is they've started to allow us to think about how we can separate our application and our deployment from our infrastructure level concerns. And as a result of having these separations, we started to introduce flexibility into how we build applications, but more importantly, how we scale and run those in production. And so if you think about where we are with the container software process, we still have our base operating system, so we still have Linux, CentOS, or in our case in Windows, Windows Server 2016. This will be running on a bare metal box somewhere, or likely Azure, which has got some great support for Windows, as does Google, if you go speak to the guys downstairs, I don't know which way we are, but go speak to their booth. So we have this operating system which you expect. And then when we build and come to deploying our applications, we can build it as a container, and then that gets rolled out. And so when we look at things like our CI/CD pipeline, developers do the git push. Instead of traditionally that going to a Team City agent, which would be configured with particular versions of .NET, particular versions of Java, and we'd have to manage those if we wanted to upgrade our apps. Instead, we now do a Docker build, and that Docker build encapsulates all the instructions about how our application needs to be deployed, how it needs to be built, its dependencies. That builds the image, and then that's what we push out, and that's what we run. And so we have this middle step, which is producing this Docker image. And now previously, this was very focused on Linux, but as I said, we now have our beautiful Windows support. And this image is what gets promoted and pushed through the various different stages as we're kind of going up. And so this introduces the concept of ensuring that we've got consistency and repeatability, and we're not getting side effects between different versions of what may be running in staging compared to the version of .NET which is actually running in production. And so this is generally what I'm sure many of us are used to in the hypervisor world. We've got the hypervisor and the guest operating systems running on top of it, each of which have this overhead and this resource attached to them. And then kind of how many describe it is now in the container world, we've got all the containers running, they're all sandboxed and isolated, and they're running on top of this container engine. And each one has, you can kind of think of Docker and containers as just a glorified process manager. It's still the same processes which we're used to launching, it's still the same applications. The only difference is now that they're running in a secure sandbox mode. It's taking advantage of hooks in the kernel, separation that comes with Linux and now comes with Windows, and just defining those for you in a very nice, accessible way. Everything which we could do with Docker had been around for the last 10 or so years. It was just very difficult and very hard to work with. Docker just cleaned that up and made it more accessible. And so people generally say that this container runtime sits in between the operating system and your applications. In reality, it sits alongside. Your applications, your processes are still talking to the underlying operating system as they would before. The container engine is just wrapping it and making it easier for the processes to be managed and started. And so this is why I think containers have very similar principles and very similar properties to virtual machines. In reality, they're just processes. They have processes, and we can build these images which are encapsulating what that process needs to be able to start. And this is what Docker has made. They've made it accessible, and they've brought along a great development experience to go alongside that. But they're also realistic. Docker knows that it can't answer every single problem and try and invent and solve every single part of the production story. So instead, they have a mindset of batteries included but removable. So if you have certain very interesting networking requirements, or you have very interesting expensive storage devices, Docker knows that it's probably not the best person in order to be able to solve those. There's going to be companies like HP, there's going to be EMC and Dell, which will solve and create very unique targeted solutions in order to solve very unique high-end problems. And so Docker's made it accessible. They've made it very plugin driven, and so you can swap out and interchange certain parts of the software stack in order to meet your requirements. But fundamentally, there are three concepts. We've got the containers, which are fundamentally running processes. We've got Docker images, which are fundamentally layered zip files. It's a zip file of everything your process needs, from the operating system up to your packages, including your application and your binaries itself. And then you've got the Docker registry, which is where these images sit. And this bridges the gap between like your CI server and your build servers to production itself. And so when you say Docker run, it goes off to the registry, grabs whichever version you need, and that is what gets downloaded and launched. And so this is what we have with Docker. And now with the advantage of Windows, the Docker itself has been extended. And so taking advantage of the multi-architecture and multi-builds of Golang, you can see certain aspects of the Docker source code have been prefixed. So it says that this is part of the Windows build. Looks skills, but we've got some really interesting kind of abstractions that Docker has introduced, and also Microsoft. So Microsoft have completely done this in the open, more or less anyway. And so you can see things like a Go, Windows, I/O abstraction. And so you can see that Docker is trying to work and collaborate with Microsoft in order to build something which feels very natural and coherent to what the rest of the Docker story is. And as such, we get a very natural and seamless experience from a development and production, because it's actually part of the engine itself. It's not an add-on, it's not a fork, it's not some out-of-date build. Instead, it's embedded and it's integrated into the entire Docker process and the build process and the testing phases and everything which they go through in order to release their applications. And so Docker has made effort, Microsoft has made effort to make it feel natural and consistent with the Docker experience. And alongside that, obviously, the Windows needed to be updated in order to be able to support these container concepts. Microsoft have tried for many years in order to have containers as part of the operating system. They've tried secure operating systems, different research projects, and it's only now with 2016 that they finally managed to introduce being able to have processes which are sandboxed and locked down and secured in different ways, and they're abstracted and sandboxed from other things running on the system. And as part of this story, they needed to add different aspects to the Windows operating system as a whole. And so there's 4 key concepts which came with the introduction of Windows Server 2016. We have Windows Server Core and Windows Nano. These are new operating systems designed to run inside of a container. And these are bootstrapping your process and giving it all of the APIs that your process needs as if it was running on a Windows operating system virtual machine itself. And then in order to manage the processes, we've got Windows containers and Windows Hyper-V containers. They work and operate very similarly. The main difference is that Hyper-V containers have a more advanced security model around them. And we'll get more into the details as we progress towards the end. But just understand that there are 2 different models, but in reality, they work exactly the same way. They run the same processes, the same images. Hyper-V is just in a more secure mode. And the architecture of Docker and Windows containers feels very consistent, very coherent to what we saw before. We have our operating system, we have the Windows kernel, which has got all of the hooks that containers need, and then the Docker engine will talk to the Windows kernel in order to launch processes such as SQL Server, ASP.NET applications, IIS, etc. And as I'm sure some of you are aware, with Linux containers, the Windows kernel or the Linux kernel is shared. Every single process is using that shared same kernel, and we're taking and trusting the security which has been built in to make sure that the applications can't communicate and they can't break out and interfere with other processes. Now, in certain requirements, this does introduce some concerns. There's no known zero-day outbreaks at the moment. There's no container breaches, but it still raises some uncertainty and some question marks. And this is where the Windows Hyper-V container comes in. It's specially designed to deliver a separate kernel from the other containers which are running on the machine. And so you can guarantee that there's isolation because it's been wrapped inside of a Hyper-V virtual machine. And so now we can be confident that our SQL Service process, while it's still running in a container, is running on a different kernel inside of a virtual machine, just as we would run SQL Server natively. The main difference is that we have the Docker images, the Docker workflow around that, and this Windows Utility VM, which has been added, is super lightweight. It starts in milliseconds, it takes barely any overhead, and so you can't really notice any performance impact in like running a guest operating or a traditional virtual machine. Instead, it's just there in order to be able to offer this separate Windows kernel. And so the reason this is important is that generally Windows containers and Linux containers are secure, they're effective, they're highly scalable, etc., and all the benefits which I'm sure many of us know and love. These Hyper-V containers comes in where you're dealing with scenarios such as shared hosting. So if you're running Azure or Heroku or something like Katacoda, you may have code which is completely untrusted, and that code may be maliciously targeting other parts of your system. Now, if you're running something like Azure, that could be potentially dangerous because it could potentially competitors which are running on the same machine, other different government agents, other things which probably don't want to be accidentally sharing information. And again, multi-tenancy, where you may have customers which you're hosting, you don't want them to be able to interact or interfere with other code which is happening on your system. And so this is where you have that added value of Windows Hyper-V containers. In the Linux world, you may have come across a concept from Intel called clear containers. It's the same concept and the same approach. Clear containers, again, wrap a Linux process inside of a very small, lightweight virtual machine in order to be able to deliver that separate kernel, and Windows Hyper-V containers are delivering the same concept. So we have these 2 runtimes, and so our application now needs, in order to have something which runs inside of the container itself. And so the first way to do this is Windows Server Core. Windows Server Core is nearly Windows 32 compatible API, which means it's got all of the lovely parts of the Windows kernel, which are still in there. It's got all of the functionality and applications which you would expect from Windows itself. It almost works in exactly the same way, and you can use existing tooling, existing packages, in order to be able to run your applications. As a result, because it's Windows and it's pretty much got everything that you would expect from a Windows operating system, it's also rather large. The base images are roughly 10 gigabyte in size, and so you do have that initial dependency and that initial hit when you start playing with containers and start deploying them. But remember, Docker images are layered, and so you only need that one copy of the operating system on the machine. It's not like you're having to download this 10 gigabyte operating system every single time you roll out an image. Instead, you just need that one layer in place, and that will be served and repurposed for all of the different containers that we're deploying, which we'll see more in a moment. On the flip side, we have Windows Nano. Windows Nano is a new, shiny operating system which has been completely stripped out. It's down to the bare essentials of what Windows really needs in order to be able to run. And so we're talking things like clustering, storage, I/O, networking, the .NET framework itself, etc. And so it's tried to get it down to something a little bit more reasonable and a little bit more size that you would expect from something comparable to the Linux world. And as a result, it's about the 20th of the size. And so Windows Server Core, roughly 10 gig. Windows Nano, more a gig in size. And Windows Nano, you may know that Microsoft made a big deal of this. It's going to be like the future of how operating systems run on Hyper-V. They've recently had a change of heart. And so now Windows Nano will be solely focused on supporting Windows containers and supporting applications running inside of a container itself. And the reason they do this, it allows them to reduce it even more. And so they're now targeting Windows Nano to be more like 70 meg or 80 meg in size. Still have all of the same Windows support, or support things like .NET and existing Windows binaries, but that much smaller, much reduced footprint, even more than what it is today. And so you can see that Microsoft are still innovating, still trying to improve this story of Windows containers, and they're progressively getting better and better as they go. And when you think about which one you should pick between Windows Server Core and Windows Nano, I make the analogy to Linux and how we have that. So we've got Ubuntu and Alpine. Ubuntu is like the operating system everyone knows and loves. It's got package managers, which everyone's familiar with. It's got a very well-established API. And pretty much you can take any Linux application, run it on an Ubuntu box or an Ubuntu container, and it will work. The side effect is it's slightly larger and slightly bigger because it's got more API support. And this is similar to Windows Server Core, where Windows Nano is similar to Alpine. Very small, very focused, very streamlined. However, you may have to have some modifications to your application in order for it to run effectively or run properly in order to be able to build. And this is where I see the mindset of the two differences. So Windows Server Core is more for your traditional applications which you don't really want to modify. You just literally want to pick up and deploy as a container. Where Windows Nano is for modern. It's for your .NET Core applications, which you're actively working on, and you can spend a little bit more time optimizing and making sure that they run effectively. And this is the differences. So how does that actually look in reality, and how do we start playing with these cool technologies? So the first thing we need is Docker. So we need the Windows build of Docker on Windows Server Core 2016. And so using the beautiful PowerShell, we can install the provider and install the Docker package. And that will give us everything which we need in order to be starting running Windows containers themselves. In reality, if we went to something like Azure, and that's where we're running, they have already got templates and machines which have been pre-configured and set up, and so that they can run containers out of the box, so they don't need to go through this additional step. And from the viewpoint of a consumer side, everything looks and feels consistent. We still have a Docker client. This has got the commands which we can run, and that client can now talk to Windows or Linux machines. One point to note before we get into details is the Windows Linux subsystem, which was introduced in Windows 10. This is completely different to Windows containers. This is an awesome approach so that you can run Linux binaries on Windows without natively. This is a different concept to Windows containers. Windows containers allow us to run native applications, i.e. native Windows binaries. And so they're solving two different problems. It's not like we're shoehorning on and translating Docker Linux images to run on Windows. We're talking about full support. So what is this Windows Docker image, which we all know, which we can all build? So we need our base operating systems, as I said. We need that for the support so that our applications have something to run inside of a container. And so we've got Windows Server Core and we've got Windows Nano. And these just sit as normal images on our machine. And you can launch them as you would any other container. So in this case, on my blue screen, that's my host. I'm running docker run Windows Server Core and running a command line. And then within our container, in the black screen, we have a command prompt. Separated, isolated, sandbox to everything else running on our system. And so my host, you can see some different scripts, Windows Azure folders. Yeah, that's not visible in my container as you would expect. Now, what's actually happening under the covers is a little bit more than what you would expect if you looked at what's running inside of a Linux machine. Windows is still Windows at the end of the day. And so there still needs to be processes which exist in order to support the applications and the processes which are running. And so we'll still see, if we look at what's running inside of a container, things like svc host. We'll still see PowerShell running, which is the process which launched it. Other things like trusted installer, etc. These are there because processes expect and assume that these commands will be there. And so Windows in itself has to have these things running in the background in order to be able to support it. So this gives us that layer and that infrastructure and makes sure that anything running inside of a container feels natural and feels like it's running on Windows, because actually it is. It's a full Windows installation. And so we're trying to think about what a good example would be. How can we demonstrate that this is, how this will actually work in reality? And so I tried to find an example which is representative of certain applications which I've dealt with in the past. And the one which I came up with was a beautiful ASP.NET MVC 2.0 application, which John Galway, Scott Hanson, and a few other people built and released in May 2010. So it's been sitting there on Coplex for the last 7 years. It's not been touched, it's not been really updated in any way, but it's got everything which the application needs, it's been built. So let's see how we can take this existing application and run it inside of a container and then use the benefits of Docker that it brings. So the first thing we need is a virtual machine. So in this case, I'm using Azure. Azure has got great support for Windows containers, as you would expect. And it's a much quicker way that if you want to start playing and experimenting, then you can use Azure until Katacoda has released its Windows container functionality, which would have been this week if I didn't have Australian Wi-Fi. But never mind. Windows and big Windows Australian Wi-Fi do not mix and make for a happy relationship. So we now have our virtual machine. It's got everything which we need. So we need to bring it up to a certain standard. For this, I use Chocolatey. Chocolatey is awesome. It was a revelation. I hadn't come to Windows for quite some time, and so I didn't really have a chance to use it. But by using it, it is just like the best way to set up and install everything which Windows needs. And so if you haven't played around with it, I definitely recommend it. But this allows you to do things like Choco install Docker. This installs everything as an alternative way than the packages, which I said before. And this will give us the Docker client, the server components, and we can now do things like Docker PS and Docker images. As I said at the beginning, you can see the sizes. Windows Server Core, 9.4 gig. Windows Nano, 800 meg. And then hopefully that will go down to more like 80 meg in future releases. So one point which I want to highlight, which is the problem with this screenshot, is the use of latest tags as a slight departure. Latest tags are very problematic because latest is a moving target. you never quite know what latest is pointing to. And so when you actually look at what's available for the operating systems, everything has a build tag, and everything has a build number from Windows. And this is very similar to if you download the ISO or download the ISO from MSN. Everything has particular builds and particular patch versions. And this is what are actually being pushed and released onto the Docker Hub itself so that you can build on. And so while latest will definitely give you the latest, greatest Windows build, it doesn't give you very good insight into what version of Windows that is. It doesn't tell you what patches are being applied. It doesn't tell you whether it's Windows 2016, i.e. the existing one today, or whether it's the new shiny Nano server which is going to be released. It's a more opaque. So instead, I always recommend that you pick a particular version, set that version, so you have a known starting point to start building your images on. And so when you actually build and do it correctly, instead of just downloading the latest, you pull a particular version, and then that will download the latest updates, the latest security patches that Microsoft have rolled out as part of the image. Now notice in this version, we have Windows Server Core, which was 5 weeks old, which was 9 gig. When we went and updated the particular version of Windows, it's only downloading the latest layer. So it's only downloading the security updates and patches that have been applied based on what your system doesn't have already. And so in this case, we're not downloading the full 9 gig again. Instead, we're only downloading 900 meg, which encapsulates all of the security updates that have been released and the new builds since the last time which we pulled. And so now we can be confident that we're building from a known image. We know the security updates were included, and through when Microsoft do another Patch Tuesday or roll out some updates, we can pull down the latest image, update the Windows version number, and again be confident that we're starting from that secure base and that secure foundation. So just like with Linux containers, we still need a Docker file. This Docker file defines how our application needs to be built and needs to be defined in order to run. And so in this case, we're defining our base image of Windows Server Core, and again, given a particular version number so that we can be confident about what patches have or haven't been applied. And because it's now in Windows, we can use things like PowerShell. And so we can use Windows features and PowerShell features like install feature, in this case, install the web server. Web server being IIS. And so if you build that, again, using exactly the same APIs and conventions that we do with Linux containers, we can say build, give it a nice friendly name, in this case IIS, and that will go ahead, that will install our IIS on top of our Windows, and we'll now have a container which has got the Windows setups and IIS running. Thankfully, Microsoft has also sorted that this is probably a very common use case, and many people will probably want IIS as a dependency for their applications, and so they have built a pre-image that you can use as your base image so you don't have to go down and install IIS each time you need it. And again, when you look at the tags, Microsoft is very explicit that there's Nano versions, there's Windows Server Core server versions, depending on what your application needs in order to be able to run. And it's got the build number included there. So you can know what version you're building on and what releases have been included. And so now we can use that as our foundation. We can say from IIS, in this case, Windows Server Core, because it's ASP.NET 2.0, it's probably going to need some more Windows functionality than what Windows Core does, so we can't use Nano, or at least I assume we can't at this point in time. But now we've got IIS installed, and so now we can start customizing the container based on what our application needs. And so again, it's ASP.NET, so we're going to need to install a Windows feature, we're going to need to install the .NET 4.5 ASP.NET framework, and we need to configure the ASP.NET and the .NET framework itself. And so this will go ahead, and as we're building up our container, we'll install these requirements. So now it's as if we are, so now we are automating the configuration of Windows itself. And so something which I'm sure is in many of our build scripts for our deployments, We can remove the default IIS website because it's no longer required. We can make a nice directory for where our application needs to live. And then we can create a new IIS directory, set things like the application pool, the port numbers, and the physical path about where our application will be served from. And so now as we're configuring our image, this is now configuring IIS to make sure that everything is in place as you would expect. So that other people know how to launch the application, we can say expose the application is running on port 80, so we know what ports need to be made available. And then finally, we copy over our source code. And so thankfully, the release which the team did for Nerd Dinner was already pre-built, and so we don't have to go through the build process. We can just take the existing built binaries and copy that into the directory which IIS expects, and we can start serving our images. So just as you would expect from Linux, it feels very same when you run a Docker build on Windows. Run through all of the different commands. We can see that it's running IIS, configuring everything which we need, and then we can do a beautiful Docker run. And because we're on Windows, it will allow us to run the Windows container. We can expose ports in a very similar way, and now we have our beautiful Nerd Dinner application running, which had not been modified, it hasn't been changed, it hasn't been touched from the last 7 years, but we can effectively and easily Dockerize that and deploy it using Docker APIs and then scale that out for our application. So this is now running as a Windows container. So again, the normal standard containers which we all know and love. If we wanted to run this as a Windows Hyper-V container, we simply define the isolation which we expect. And so we can say that the isolation needs to be Hyper-V. And so when that container starts, it will be wrapped in this very small, lightweight virtual machine. It will run on a different kernel and can run in that slightly more secure mode than what we had before. And this is now the difference between running a Windows container and running a Hyper-V container. The image itself doesn't change. The way we launch containers doesn't change. We can just set this additional isolation mode. And once we've got our image, it's fixed. Nothing changes. Everything which we had before stays the same. And if we wanted to roll out a new image, we'd rebuild and we'd push it out and we'd release our new image. And this kind of feels a little bit like what I did with Nerd Dinner was lift and shift. It is. I picked up an existing application. I didn't need to change it, but I could effectively and easily run it inside of a container. And Microsoft and Docker are very aware that this is probably going to be the journey that most companies are taking. They're going to take existing Windows virtual machines, which companies don't want an easier way to manage, probably remove and reduce some of the license fees, and run them now inside of a container. And so to make this easier, they've got a tool called Image to Docker. Image to Docker will inspect a existing Windows machine. It will inspect how it's been configured, what packages, what Windows features are installed, and as a result, it will build you a Docker file, which is representative of the configuration of that virtual machine. And then you can build that as a base image, use that as your starting point, and then deploy your application on top of it. And so when you can see here, when we installed it, it's running things like get Windows artifacts, and it will know that it's got IIS, it's got MSMQ, it's got SQL Server configured, and all of those will be encapsulated and put into the Docker file itself. So this gives us a really nice way that we can still continue to embrace this lift and shift mentality, and there's tooling around it to support it, and giving us this foundation to build upon and move applications into this new world. But one thing about having this immutable and unchanging image is what about Windows updates? Now, if it's a full-blown Windows operating system, then Windows updates will be happening in the background. And then we kind of break that kind of mindset of containers. If it's constantly updating, then everything breaks. So this is one of the bits where Windows Server Core and Windows Nano are slightly different because certain things have been disabled because they don't need to be running or shouldn't be running inside of the container itself. So one of these is Windows updates. Another example is Windows Defender and antivirus software and malware detection, etc. because that should be happening on the host and not inside the container itself. So instead of Windows updates, this is why the build number of the Docker image which we're using is so important, because that build number represents what updates have been applied. And so we can't expect Windows to keep itself up to date because Windows updates aren't running. We want that immutability from our Docker image. So instead, we would, when a new release comes out, we'd change that build number, roll that out, and then be confident instead of a thing changing under the covers. Docker and Microsoft have made it somewhat easy. So they've got UIs that if you do something like Docker inspect, it shows you the hashes of what's running. So if you did an inspect inside production and said which security updates have been applied, it will give you the layers, and then from the layers and from the hashes and the shards, you can get back to the original Windows version number, which was actually used as that baseline and that foundation. And again, from a security auditing point of view, and monitoring and making sure that you're always up to date, this gives you some visibility if you accidentally lose that Docker file or the Docker file isn't available. Just like we have with Windows containers, with Linux containers, we can persist data. So we can use the same approaches. We can mount in directories from volumes. So like source on our host maps into destination inside of a container. So if we're running things like SQL Server and it's writing and persisting data, that can still be mapped onto a host using the same approaches that we have with Linux. And similarly, we can start limiting and restricting processes and security around that container. So in this case, limiting how much of the CPU shares it should have, limiting the memory which that container can use in exactly the same way that we can in the Linux world. And for those who are more familiar or want to combine Docker and the build processes or deployment processes with existing scripts, there is a PowerShell API. And so you can do things like get container image, which is the same as doing Docker images, and that will give you back all of the information, but as a PowerShell object and as a PowerShell result. So you can start piping this into other scripts and other processes. And the same with things like launching new containers. So instead of doing Docker run, we can say new container. It's a little bit more verbose, but it does allow us to integrate and combine with other scripts in our system. So from this point, we have Nerdinner. We've successfully built it based on IIS and Windows Server Core. It launched and everything seemed happy. But we also have the dependencies and other things that need to be running inside in order for that application to work as expected. And one of those is SQL Server. So thankfully, Microsoft have also made it possible to run SQL Server both as a Linux container after migrating the source code, but also now as a Windows container. And so if we want to take the SQL Server, which we all know and love from Windows, that can successfully run as a Windows container on our servers. And they also have Windows Server, SQL Server for Windows Express, SQL Server Express, if we want to run it for development purposes, for example. And this works in exactly the same way we'd expect from running Linux containers. A few advantages we get, we need to set a password, such as password. We need to accept the end user license agreement, because at the end of the day, it's still Microsoft and it still has things like tick this box in order to continue installing a process. That's a little bit difficult when you're running a container. So instead, you have to set the environment variable to yes to indicate and simulate ticking the box, which no one ever reads. So when we launch it, we'll download all of the Windows, the SQL Server image and all of the layers, and we can do things like Docker logs and view the output from SQL Server. In this case, it started. It kind of failed the password complexity because I said password, unsurprisingly, and so you have to give it something a little bit more secure and long in order to be able to get it to successfully start. But once it started, we still get that same visibility and insight using Docker logs. You can see that SQL Server started. When it booted up, it changed the SA credentials based on what we set in, what we passed in, and now we can use that from our Nerdinner application to access it in exactly the same way as if it was installed on a host somewhere. So we now have these two containers. We now need to be able to start them and stop them and manage them effectively. And so this is where Docker Compose comes in. Docker Compose is now has a Windows binary, so it runs natively on Windows. Using Chocolatey, it's very simple and easy to install, and it has exactly the same structure which we'd expect. So we can define our two containers. We've got SQL Server, our database running SQL Server. We can define the ports, the passwords, the environment variables, and then we've got our Nerd Dinner application at the bottom. And we do Docker Compose up, and then that will bring up everything and start all the processes which our application needs. And we have our application. When I first did this, I thought the team had done a better job than kind of like what the box is. So when you're prototyping and playing, remember that IIS and Edge on Windows Server run a slightly different, more secure mode, and so they basically block everything and treat it as if it's running, the application itself detected as if it was running on a mobile device. So once installed something more pretty like Firefox, it operated and it worked in exactly the same way, and we had the entire application successfully deployed, which I was pleasantly pleased with, and we brought back the awesome days of 2010 applications. And like we can start running Nerd Dinners again, which would be great. So in order to make this accessible, you can set the firewalls rules, open up port 80 in IIS, etc. In Azure, and that will operate in the same way. And we can then, because we're using a consistent API, we're using a consistent experience, our CI/CD process for Windows looks almost identical to what it would look like in Linux world. We have our GitLab or CI/CD, TeamCity, etc., which starts the build. The build is Docker build, which encapsulates all the Windows functionality which we need, produces that image, we push it up to our registry, and then use something like Docker Compose in order to be able to download it and start it on our server. So if it's similar, what is the actual difference? So apart from obviously we can run Windows binaries, is how the kernel virtualization works. So looking under the covers of what's happening on Docker and Linux, we have things which we know and love, like the Docker client. This talks over an API to the engine, and the engine is broken up into different parts which solve 13 different problems. So like our networking, our containerd, which is an abstraction over the Linux APIs, and then the security from Linux and how the sandboxing works is made up of things like C groups and namespaces and other capabilities that go into making a container be contained. And this is what Docker is configuring. With Windows, it looks and feels very similar. We still have things like containerd, we still have lib networking for configuration, for configuring the Windows networking, and we still have things like control groups and namespaces and layering capabilities. It's very similar, it feels very consistent and coherent. The main advantage, main difference is that we've got this compute service. And this compute service is an API into the Windows kernel. And so it means that while Docker is the only one launching containers today, going forward, anyone can write a container runtime, a container API to launch containers directly against the Windows kernel. And so if you particularly don't want to go via Docker, or you want to play around and customize it yourself, then you have the capabilities and the APIs in order to be able to do that. And so Docker and Microsoft aren't interconnected. They're not. Microsoft isn't dependent upon Docker in order to deliver this container support. Instead, anyone can write a client on top of it, which I think is really cool. In terms of undercovers when it comes to Windows Hyper-V, again, we've got this problem of shared kernels, and we've got this problem of the security restrictions. And so the Intel clear containers is what's on Linux. In Windows, we have Windows Hyper-V. And so we start this Windows utility. So when your operating system boots up, and this is how it gets its performance, alongside booting up Windows, it also boots up the utility VM. Inside of Hyper-V, boots up Windows utility inside of Hyper-V. It then takes a freeze and a snapshot of that virtual machine and basically puts it on a pause. And so it's running, it's got everything it needs, it's just not taking up any resources. When we run our container, it takes a snapshot or a fork of that virtual machine, which is running, but in a frozen state, and then splits it. And so the only additional memory allocations that that virtual machine is using is actually the bit which is required for the container. All of the other memory is in this frozen shared snapshot state. So very similar to doing copy on write, if you're familiar with how that works, where the only things which you are persisting is the things which have changed. Windows and the utility VM is basically doing that, but for memory. And so this gives it that really fast launch time, but also makes it really lightweight. And it's invisible. From the container's point of view, they can't tell that they're in this separate shared, in this separate virtual machine. But if they do manage to break out, and an attacker does manage to get a 0-day, we can be confident they can't interact. If they write anything to that virtual machine, it's instantly forgotten. And when that container stopped, it completely gets removed from our system. And so this allows us to be secure, it allows us to build the images, but what about developers? Like, we don't all want to go back to the days of running a server operating system on our laptops in order to be able to be confident that what we're building is what we deploy in production. And so now we have support for Windows. In Windows 10, we have container support, and so we can build and deploy and test Windows containers on Windows 10 in exactly the same way that we do on Windows Server 2016. The way this has happened and the way this works is by using that virtual machine, this Hyper-V functionality. And so when you run a container on Windows 10, it's wrapping it inside of this Hyper-V isolation mode, and so that's what gives it the kernel that's required to have Windows container functionality. And so this is how we can test and experiment on different operating systems and different versions of Windows, because that shared kernel is being repurposed inside of Hyper-V. When you're on Windows 10, it looks and feels very similar to what we would know and love. So this is Linux. If you're running things like Docker for Windows, there's now an option. If you go switch to Windows containers, that will make the client, instead of talking to the Linux VM, talk to the Windows VM. And so when you do things like Docker versions, you'll see that it's now talking to a Windows architecture. And if you list all the images, you'll have things like Windows Nano, which has been downloaded. And so this allows us to experiment and prototype and build and construct both sides of the Linux and Windows world. So when it comes into production, we don't want to go and remote desktop into every single Windows machine and do a Docker run, because that's going to be error prone and time consuming. Instead, we want it more of a container orchestration to solve that problem for us. So Docker have their own solution called Docker Swarm, and this allows, has got support for Windows containers. But more importantly, it allows us to have hybrid modes and hybrid support for both Windows and Linux containers running within the same cluster. And so in this case, we're deploying two services. One is a Windows HTTP service. We are specifying a constraint. We're saying that this container should only run on operating systems which are of type Windows. It's a Windows container, it's a Windows binary, so we need Windows there in the first place. And so when we deploy and tell Swarm to deploy this container, it will search and identify Windows machines which are the most appropriate to deploy our application, our container onto. And then on the flip side, when we come and deploy our Docker service, we can set another constraint saying deploy onto Linux, and that will deploy onto Linux modes. In future, it would be nice if Swarm understood the architecture of each images. It knows that one is built for Windows and one is built for Linux. So hopefully in future, we can remove this definition of the constraint. But once these have been deployed, they're all running over an overlay network, and so they can communicate and they can talk internally as if they were on the same machine, but they're using cross machines, different architectures, but from the viewpoint of the application, it's all a seamless, lovely experience. And so Swarm has this hybrid mode built in today. If you were there at my talk yesterday with Kubernetes, Kubernetes is a more advanced scheduler. It's got more capabilities than what Swarm does at the moment, at least. And it's driven by some of the thoughts and some of the opinions which came out of Google before it donated it to the Cloud Native Foundation. Thanks to work done by Microsoft, Apprenda, and Red Hat, which I thought was a great collaboration and showed the new change in the Microsoft landscape, they've collaborated and added support inside Kubernetes so that can also deploy Windows containers. And so again, very similar to how you have a hybrid Swarm cluster, you can now have a hybrid Kubernetes cluster, which can manage both your Windows containers and your Linux applications through this single control plane. This allows for scenarios such as deploying SQL Server applications using SQL Server on Windows, but then having your nice, modern, shiny .NET core applications deployed using Linux and using that scale out, but having everything in this one single deployment approach. There's also DCOS, which has got lots of integration into Azure, and I think under the covers is powering the Azure Container Service. And this is where it's getting smart. So as I said, with Swarm, you have to define the constraint. With DCOS, you don't. DCOS has host fingerprinting, and so it understands the type of workloads which you're asking it to run, and it will find the most available host for that machine to run on. So if we take 3 examples of tasks, we've got Linux, we've got Windows, and we've got something portable like a jar file, which can run on both Windows or Linux, thanks to the amazing JVM. You give it into the DCOS scheduler, which is Marathon and Mesos under the covers, and then it will manage and automatically detect which host that workload should be run on automatically. So, for example, Linux should only run on Linux nodes, Windows only on Windows, but something portable like Java, it will pick the most available box based on available resources and other workloads happening. The the Azure Container Service also has support for Windows containers. And so when you launch it up, you can specify that you want hybrid clusters of both Linux and Windows machines and have that capabilities built in. And so now we have this really great approach where we get this hybrid approach. We can deploy things consistently, whether it's on Windows or Linux. We can take existing applications, move them into this container world, and now deploy them in exactly the same way that we're deploying other applications using things like Swarm or Kubernetes. But where does the future hold, and what does the future look like for containers? So we have Windows, we have Linux, but we also have IoT. We have ARM devices, we have Raspberry Pis, we have other things. And cool companies like Resin are building experiences so that you can deploy Docker containers in exactly the same way, but targeting ARM and IoT devices. And so now we have that consistent experience, but we can target everything, including our small micro devices. And they have really great demos where when they do a Docker deployment to one image, you can see it rolling out across other IoT devices in a cluster, in kind of like a swarm mode, one of which is literally flying drones. They deploy an image to a flying drone as it's going around, and that will automatically update the other versions of the flying drone software running as they're all flying within the cluster, which is the definition of zero downtime deployment. So we have this, we have IoT devices, we also have SQL Server running as a container. So we don't have to go through the same process and ticking 15 checkboxes in order to have SQL Server running. Instead, we can deploy it as a container. But it begs the question until how long does it take until we have things like Visual Studio running as a container? Why do we go through the steps of downloading 4, 5 gig images to then spend another hour having it installed and optimized for our solution, where if it's running inside of a container, that could be done in advance? Instead of having to download the updates, which could potentially, which again takes time and interferes with the system, we could download the latest layer, just as we do with Windows containers and Windows Server Core today. And so changes can be much more reduced. We get much better build time and much better experience, but also they're sandboxed. And so one version of Visual Studio wouldn't interact and interfere or modify the registry of other Visual Studios. And so we can run things in parallel, side by side, because this is the whole nature of what Windows containers and what containers are designed for. And this gets us to a point where we have everything being deployed as a container. We have our Windows applications, we have our Linux applications, we have our development experience and our development scripts, and we even have our door sensors and other IoT devices, all going through this Docker container, Docker images, and Docker run style experiences. And thanks to the cloud and services like Swarm and Kubernetes, they can be deployed anywhere. We can have hybrid clusters, which are distributed across multiple clouds, which all manage our workloads. And so if we lose a region, or if we lose a data center, or even an entire cloud provider, our systems will still run, still maintain, and still deliver the performance which we expect. So this is all a fast-moving landscape. Containers, especially Windows containers, are coming and adding cool new functionality. And this is one of the reasons why we built Katacoda. Katacoda is a free interactive platform. We've got different scenarios which explain and go into more details about what I'll talk today, and the platform where you can play and experiment and try different things out. So with that, as a summary, we talked about the 4 new concepts which were introduced into Windows Server 2016. We've got the new operating systems, which is designed to run our processes inside a container and deliver it the support and the APIs that that process needs. If we've got more traditional applications, we target things like Windows Server Core. If it's a more modern application, then we can use something which is a little bit more streamlined, a little bit more cut down in Windows Nano. We've got Windows containers that allow us to run processes in a sandbox, secure nature. But if we're running in a slightly more sensitive environment, we've got Windows Hyper-V containers to give us that additional security, give us that additional separate kernel to keep our security auditors happy. We've now got support on Windows 10, so exactly what we've talked about. The building of Windows images can happen locally. We can test and make sure that applications work, and then we can use that image and push it and run it onto Windows Server 2016. And when it comes to running it in production, we can do things like Swarm or hybrid Kubernetes clusters, and we'll start having that so that we just issue the workload, and then we might find the most available, most appropriate box, regardless of underlying operating system, to deploy our workload onto. In terms of the next steps, obviously Katacoda. If you want to play around with Windows containers, doing it on Azure is a great starting point. As I said, the operating systems are fairly sizable downloads, and so running it in the cloud saves your local SSD and is also significantly quicker. And we've got Windows 10 support, so if you do want to play with it locally, when you install Docker for Windows, you can switch it and say switch to Windows containers, and you can have an experiment with all the functionality which you need. If you have any questions, please do let me know. Please send me an email or drop me a tweet. And with that, thank you very much. Enjoy the rest of your conference.